Okay, let's start. First, thanks for coming. And this is before Chinese New Year. I guess lots of people are in the holiday mode. So anyway, okay. So today's topic is actually quite interesting. It's about infinity. Okay, but before that, okay. So here's the outline. I'll say something about the basic concept about infinity, and then we'll talk about some specific infinite set, for example, the set of natural numbers, and then we look at the set of the real numbers. Then after that, we'll mention something called the continuum hypothesis. So the content of this is definitely beyond our syllabus, but I think it's quite nice to know. So it's we don't need to know the details, but just like a story. Okay. So these are the outline for today. The number of slides was less than usual, but they are something quite abstract. So I hope. Okay. So if I finish too early, I hope I don't finish too early, but. We'll see. We'll see what in the end whether I have enough time or have not enough time. Okay. So before that, I want to answer some queries. Okay. So last time we talked about this a theorem by Euclid, which tells us there's infinite. So the number of primes are infinite, right? So there are lots of prime numbers. So in the proof that the proof depends on a little bit knowledge on arithmetic. So, but some people ask me after class, I assume that maybe I need to explain it one more time. I guess this class have, how to say, the spectrum of your math knowledge are varied a lot, right? Some of them are extremely advanced. Some of them are less, how to say, has probably elementary knowledge on mathematics. But I welcome questions. So this is a general education module. So I don't care about those who are extremely advanced in mathematics. So I care more about those with only elementary knowledge. So please do stop me or ask me. I am willing to spend time to explain some basic things. Okay, so, all right, so this is a part of the proof in Euclid theorem where I use some knowledge about numbers. Okay, so let's go through these basic knowledge, right? So, so in the discussion below in this slide, all numbers mentioned will be natural numbers. Otherwise, I have to say natural numbers over and over again. Okay, so first, this stroke, this bar between two numbers, it means divides. Okay, so we say that this natural number n divides natural number m. The notation is n stroke m. If the m is equal to n times some number k, right? So in other words, m is a multiple of n. Right, so this is the meaning of this divide. So let's look at some examples, right? For example, 2 will divide 6, 3 divides 6, because 6 is multiple of 2, 6 is multiple of 3, right? Now, there are some numbers like 7. 7 is a multiple only 7 and 1. So the number like 7 are called prime numbers, okay? So this is some notation I didn't explain, but now I explain it now. Okay. What's going on? Oh, okay. Okay. So here is a property about this divide. Okay. Suppose the natural number n divides m1. m1 is a number. Natural number, and n also divide m2. The claim is n will divide bracket m1 minus m2. So n will devise their difference. Actually, n divides their sum also. Okay. So now the reason or the proof is really simple. The meaning of n divides m1 is m1 is a multiple of n. So you can write m1 as n times sum k1, right? And n divides m2 means m2 is a multiple of n. So for sum k2, m2 is n times k2. Okay, I should have added for sum k1, k2. Okay, so therefore, if you take the difference, well, it's still a multiple, right? So you take the difference is equal to n times the difference of k1 and k2. So the left-hand side is a multiple of n, right? So therefore, this is still a multiple of n. So in other words, n divides the difference of m1 minus m2. Okay, so fairly simple, right? So now this is the source of the query. So we have in the proof of Euclid's theorem, we pick some prime number. It's called P sub r. This is just a number. And the capital N is the funny number of a product of some primes plus 1, right? So in particular, if you have this guy, P sub r divide n, and P sub r divide n minus 1, by this claim, P sub r will divide their difference, right? So the claim, think of the capital N is m1, n minus 1 is m2. So we have the situation that P sub r divide m1 and m2. So P sub r should divide their difference. But their difference is just 1. So P sub r will divide 1. And then we want to claim this is a contradiction. So the contradiction depends on this fact. The number 1 is not a prime. So when we count prime numbers, we start from 2. Okay, so the first prime number is 2. The next one is 3, and then next 5, 7, and so on. Okay, so therefore, if you have a prime number, it divides 2, then it's a contradiction. Okay, so some of you may ask, why don't we like, why do we hate 1? Right? No, we don't hate 1. So the reason we do not include 1 as primes is because in arithmetic there is a theorem called the factorization theorem, or fundamental theorem of arithmetic. So it says every number, give me any natural number, I can factorize them into product of primes. For example, 6, right? 6 is 2 times 3. So you start from natural number, you keep factorizing, keep taking out these factors, right? So eventually you hit somewhere you cannot factorize anymore. So you get a bunch of prime numbers, you multiply them, right? Now, in this theorem, we want to have some kind of uniqueness. For example, 6, you can write as 2 times 3. At most, you can write 3 times 2, but no other ways, right? So in some sense, it's unique up to the order, right? Now, the power of the prime is also unique. So 6 is equal to 2 times 3. So the power of 2 is just 1. Power of 3 is 1, right? Now, if you allow the prime number include 1, and then the power of 1, you can choose whatever you want. So somehow it messes up the unique factorization. And also, if we exclude 1, we do not lose anything. Everything is fine. So therefore, we do not count number 1 as a prime, right? So this is just a convention, okay. So I hope this explains the proof of Euclid. Okay. All right. So perhaps I'd better stand here. Okay. So now I have to explain why do I want to talk about infinity. Okay. So the course is called Living with Mathematics. In some sense, we are going to talk about mathematics in real life. But in real life, there's no infinity. Well, you can debate, but at least some people believe that our world is finite, right? So we have the universe is finite because from Big Bang until now is a finite time, and the universe is finite. So there's no infinity in the universe. Okay, so that's one of the view. Okay, so the infinity, you won't encounter infinity in real life, in everyday life. Okay, so, but I still want to talk about it because I like the topic. And so I quote David Hilbert. I think we have seen his picture in the last slide. He's a famous mathematician, maybe the most influential one in the 20th century. So he wrote an article called On the Infinite. So inside the article, he begins with what I just said. So it is possible the whole universe, physical universe, is finite. But mathematicians still like to talk about infinity. Okay. So the reason, okay, so he gave some reason. So he said the definite clarification of the nature of the infinite, instead of pertaining just to the sphere of specialized scientific interest, is needed for the dignity of the human intellect itself. So he really raised the level, right? So to defend, so at that time, there are paradoxes around in the world. I mean, in the math community, then some mathematician says we have paradox because we went too far. The things get too abstract, too far down the road in the infinity. We don't know what we are talking about. So they want to restrict mathematics only to the finite mathematics. So anything infinite will be excluded because it's dubious to certain people, right? So Hilbert, as a leader of the mathematics community, he wants to defend infinity. So this is one of his famous quote. Okay. So now let's talk about the proper infinity, right? The topic. Okay, so let's start from something simple. So we can count the number of elements in a finite set, and also we can compare the size of two finite sets. Okay, I will not define what finite set is, but I'll give you an example. Okay, so for example, this is a finite set, 0, 1. Only have two elements, so it has size 2. So remember that we use the two bars indicate the size of a set, right? So last time when we talk about counting in finite set, we have seen this. So the size of this set, 0, 1, is 2. Also, let's say take the set of 3 elements like A, B, C. You can easily count. This has 3 elements, right? So you can compare. You can find the number of elements in the sets, and you can compare the size because you know one has 2, the other one has 3, so you know which one is bigger. Okay. So maybe I'll. Sorry. Then I'll move to look at this screen, so I cannot look at the big screen. Okay, so the question is, how about infinite set? Okay. Now, so more precisely, we want to ask, do infinite set have size? Can we talk about, is it meaningful? Does it make sense to talk about size of infinity, right? And can we compare their sizes? So this is the question. Okay. Okay, here's the great guy who invented set theory. Actually, his achievement, okay, why do we care about set theory? Actually, study set theory is study infinity. So it is infinity that is more important. Okay. So Georg Cantor is the father of set theory. So he has the whole theory of infinite numbers. Okay, we'll see. We'll see the most basic part of his theory. Okay, so here, the notation, the concept was very simple. So how to compare two infinite sets, right? So the key idea is we say two sets have the same size if you have a perfect matching between their elements. This is the idea. Okay, so now if you read popularization books, there are lots of interesting examples to illustrate this, right? So, for example, some book will say there's some tribe. For example, there's a tribe called Pará in Brazil. So in their language, they never have a number bigger than 2. So bigger than 2, it becomes many. But if you have lots of numbers, they will say many, many. And so the setting was, if you go to the tribe, then give them something to compare. Some textbook or some storybook will say, you know the stone, when people play Go, you have stones. One basket of white stones, another basket of black stones, right? So certainly each basket has more than 2 stones. So you pass it to the people, primitive people, ask them which one has more stones. Okay, certainly they cannot count the number of stones because it becomes many. Both of them are many, right? So now can you help them find a way to decide which one has more stones? Well, we use the idea, right? So the clever people, although they are primitive, they are smart. So they will match. They will take one stone from the white, one stone from the black, throw it away. Take another pair, throw away. And then until one of the basket is exhausted, right? So if they exhaust at the same time, they have the same number of stones. If one basket finishes earlier, then he has smaller, right? So it's quite simple. The idea is simple and natural, and it works. Okay, so now think. Okay, so this is one often used example. The other often used example is you ask the number of noses in the lecture theater, and you ask the number of mouths in the lecture theater. I do not need to count how many noses, right? I do not need to count how many mouths. I know that they have the same number because each person, if you have a nose, you have exactly one mouth, right? So because the number are matched, so they are the same. Okay, so well, you read lots of story like this, but okay. So these are the informal examples. To make the idea formal, we have to use some mathematical terms. Right? So let A, B be 2 sets. We say that A and B have the same cardinality. So the size, cardinality is a fancy word for size. Okay, same cardinality written as the size of A equal the size of B. If there is a bijection from A onto B. Last time we talked about functions, right? So we say the intuition between bijections are you have a perfect match, right? You have a function from A to B so that every point in B are hit and no 2 arrows sent from A hit the same target. So somehow you can match the element in A with the elements in B, right? In that one-one correspondent way, okay? So this is the definition. Now, this definition will certainly work for finite sets. It also work for infinite sets. So the example I give you for the stones is like for finite sets, right? It also works for infinite set. Gödel once wrote an article to explain what is continuum hypothesis. So he gave a explanation why this kind of definition is reasonable. So he was saying, suppose I want to compare two sets, A and B. Now, the counting of elements in A doesn't depend, so the elements in A, when I do counting, it doesn't depend on the element shape or the physical properties, right? So either it's red or it's blue or it's square or it's round. It doesn't matter. It's an element, so I count. My counting doesn't depend on those physical things. So then let's assume we can change the physical things, right? I can change the color of the object, and the counting doesn't change, right? So you agree, right? Okay. So now I have two sets, A and B. I can match their elements because by definition I have a perfect matching of the elements. Right? Now imagine you have this magic. You can change the shape, or so suppose A has square plastic, and B has round, I don't know, clay. Okay. So now suppose you have the magic. You can change the square to round, and you can change the plastic to clay. Okay. According to the corresponding elements. So you change this, change this, change this, change this. Change every element in A, follow the physical property of its corresponding element in B. Okay, right? So then A become exactly the same set as B, right? Because I change it just like that. So therefore, if they have the same size, if they are the same set, they certainly have same size. But we agree that the counting doesn't depend on the physical properties, the color or the shape. So therefore, this is an explanation. Well, there are lots of explanations, but this one is interesting. So okay, but the one-to-one correspondence between the numbers, people noticed it long time ago. So in the 17th century, Galileo, the famous physicist, right? So he noticed this. So this example actually is due to him. So he observed that if you look at the sets, the positive natural numbers, and they are squares, right? So 1 square is 1, 2 squares is 4, 3 squares 9, and so on and so forth. If you observe these, you can easily have a perfect matching between them. Send n to n square. This is bijection. This is 1-to-1, and this is onto, right? So by our definition, these two sets has the same size. Right? Galileo noticed this, but Galileo didn't discover set theory. So what stops him? So here's Galileo's observation. So it cannot be denied that there are as many squares as there are numbers, because every number is a square root of some square, right? For example, 2 is a square root of this 4, 3 is a square root of 9, and so on. So he noticed this one-to-one correspondence. So if you notice this one-to-one correspondence, the number of positive integers is the same as number of squares. But however, he immediately said, yet at the outset, we said there are many more numbers than squares, because the larger portion of them are not squares, right? You see, you're counting this, so 3 is not squares, and then there are lots of numbers between 3 and 9, they are not perfect squares. Galileo said not only so, but the proportionate number of squares diminishes as we pass to larger numbers, right? The gaps between n square and n plus 1 square, there are more and more numbers. The gap becomes bigger and bigger, right? So this is the observation which puzzled Galileo, right? So what stopped Galileo is the old belief or the principle that the whole is greater than the part. This principle is one of the axioms in Euclid's Elements of Geometry. When you study geometry, very often you look at angles, right? If one angle is part of the other angle, then the part is less than the whole. So this is another common sense, a natural idea. So now these two ideas somehow do not, they are contradictory to each other. So which one should we give up, right? So Galileo gave up this, the first one, right? He gave up the concept of infinity. But Cantor did the opposite. Cantor gave up this, the second one. So the whole is greater than the part. So he and then he has a beautiful theory of infinity. We are going to talk about. Okay, so I'll give you lots of examples about the size of infinite set. Right. So the first part is talk about the size of natural numbers. Okay. Lots of things related to natural numbers. Okay. So here's a theorem. The size of natural numbers is the same as the size of even numbers. Right. So if you understand the claim about square, you understand the claim about this. You just send n to 2 times n. You have this bijection, right? Okay, so the proof is, okay, you define a function f such that f of n is 2 times n, then this is a bijection, right? So you can see lots of part actually equal to the whole, right? So even number is part of the natural number, but if you look at the size, they're the same. Perfect squares are part of the big set, but if you look at size, they are still the same. Okay, so infinite is weird, right? So this again is a very, very famous story or famous analog. It's called Hilbert's Hotel. Hilbert is the Hilbert we have talked about several times. So here, imagine you have a hotel with infinitely many rooms, right? Like labeled by 1, 2, 3, 4. It's like positive natural numbers. And somehow this picture has everybody look like a Hilbert, right? So you have lots of Hilbert there. And then the advertisement says Hilbert's Hotel, always a vacancy. Okay. So why it is so? Suppose it is full. Now, this Hilbert comes, right? So this guy, suppose the rooms are full, and then here's one more guest. There's no vacancy. Every room was occupied, right? But the magic about infinity or about Hilbert Hotel says, so Hilbert will say, the guest in number 1 move to number 2. The guest in number 2 move to number 3. Guest number 3 move to number 4. Just shift your room, just move to your next room. Right? Now, since you see there's these things goes all the way to this blue cloud, right? So everybody will move to the next room. Everybody still have room. But suddenly, number 1 was vacant, right? So this guy can stay in number 1, right? So now suppose you have 5 person comes in. Can you do the same trick? Yes, right? So you ask number 1 go to number 6, and everybody shift 5 rooms down the road, then you have 5 extra rooms. Right? Now, why do I put this on this slide? So suppose you have infinitely many guests come in, right? Not only you have this, a line of Hilbert goes to infinity. Suppose you have a line of Cantor like this come in, right? They want to stay. Can you manage? Well, use this example. So suppose I have infinitely many people come in, where the rooms are occupied. So the manager will say, the guests in room N move to 2N, just like this. The guests in number 1 move to 2. In number 2 move to 4. Then in number 3 move to 6. Then suddenly all the odd number, the room with odd number are vacant, right? So the infinitely many people will happily stay at those rooms, right? So it's a very so infinity is very strange, right? So this is something new. Okay, so let's look at other set which has the same size as the set of natural numbers. We are interested in set of natural numbers because this is the smallest infinite set. You cannot get anything smaller. Anything smaller will be finite. Will have a size, 2 billion, 2 trillion, and so only the smallest infinity is the set of natural numbers. Okay, so now let's look at more examples, right? So the set of natural numbers turns out to be the same as the size of integers. Although on the number line, the natural numbers only occupy half of the line. But yet, by this definition, they are equal. Now, can you prove? So we can use those, like Hilbert Hotel, right? So we can use the even numbers to match the non-negative part of Z. Let me finish this transparent. I'll draw a picture on the visualizer. Okay, so we'll use even numbers to match the non-negative part of Z, and use odd numbers to match the negative part of Z. Right. So the Z is like the negative. Okay. How do I say? So if you look at the picture, the Z has infinitely many negative numbers, more than the natural numbers, right? So it's like Hilbert Hotel. Suddenly you have infinitely many negative numbers you want to slot in. So what we do is we ask the people occupy the natural numbers, move if you are in the room N, move to 2N, right? So suddenly all the odd numbers are empty, and then these negative numbers will enter the odd numbers, right? So that's the idea. So mathematically, we have to define a function which is bijection, right? So if you understand the idea is very easy. So you look at f of n. If n is even, you give it to the positive part of z. If n is odd, you send it to the negative part of z. So you can show that this is a bijection. I'm going to show it in the next slide, but let me draw a picture so that we know what I'm talking about. Good. But this is obviously too big. Okay. Okay. Here's n. Here's z. Okay. So now I want to match. I want to have this is the f I'm going to define. So if here you have 0, 1, 2, 3, 4, and so on. Right? So I'm going to use even numbers. Okay, so here you also have 0, 1, 2, 3, 4. And you also have -1, -2, etc. Okay, so now what is the f? So I'm going to use 0 map to 0. Okay, 2 maps 1, 4 maps 2. Okay, 6 will go to 3. So I'll use even numbers to cover the positive side of Z. Right? Now, these odd numbers, I'm going to settle the negative part of Z. So I'm going to use 1 to cover, to map to -1. I'll map 3 to -2, right? So the function I just, sorry. But you know what I'm talking about, right? So here, lots of odd numbers are going to be mapped to the negative numbers, right? So this one, I map it to -n+1 divided by 2. Sorry, f of n equal this, if n is odd. Okay, so what is f1? Okay, when n equal 1, I get this is 2. 2 divided by 2 is 1. So this is -1. What is f of 3? Okay, what is f3? I want to map it to -2. Is it true? So this is minus 3 plus 1 is 4. 4 divided by 2 is 2. So this is -2, right? So the function I described really is this function in the picture. So you can see this is a perfect matching. Okay? All right, so this is the this is the definition of f. I guess I spent enough time on the picture. I will not give you the full proof, but the full proof is really simple. So this is a mathematical proof checking it is injective and checking is surjective. So I guess I'll leave it to you to read. Okay, it's straightforward. Okay, so we have seen the size of natural numbers is the same as the size of integers. Now, what I'm heading now is I will convince you the set of natural numbers is the same as the size of rational numbers. Now, it's even more dramatic because rational numbers looks a lot more than natural numbers. So this is even more counterintuitive. Okay, so to do that, I have to show that okay, there are many ways of showing it, but one way, typical way of showing it is to show that the set of natural numbers has the same size of two-dimensional integral points. So I want to explain the two-dimensional picture. So I want to talk about this Cartesian product. So let AB be sets. So the product or Cartesian product of A and B is a set of all pairs whose first component comes from A, the second component comes from B. You have seen this, right? So why it is called Cartesian? Because it's named after Descartes. Descartes is the guy who invented analytic geometry. So he assigned coordinates to the points on the plane. So that's why it's called Cartesian product. So let's look at some examples. Suppose A is 1, 2, 3, B is the bracket A and B. So what is A times B? So you have lots of pairs, right? So the pair first component comes from A. So 1 is one of them. The second component comes from B. So the small a is come from this capital B. So A times B collect the pairs like this. Now what is B times A? So now the order changed because this is ordered pair. So this time you have to take first component from the first set. So you have to take the letters first. After that, the second component can be numbers, right? So you get a set of pairs like this, right? So this is an example product. Now, if the two sets are equal, the product, we just write a squared, right, as a times a. Okay, so for example, R squared is a usual two-dimensional, we call it Euclidean plane, or just a two-dimensional plane. Even you are from engineering, I'm sure you have seen this, right? And the Z squared is a set of integer grid points on the plane, right? So imagine you have R2, you pick out those like 1, 1, or 1, 2, or 3, minus 3. So these things are elements in Z squared. Okay? So now the theorem I'm going to show you is this n squared, n times n. So these are the points on the plane, two-dimensional plane, actually is equal to the size of natural numbers. Okay? So there are several ways. So computationally, this way is easier. So you can define a bijection between the n squared and n in this way. You define f maps the pair m and n equal to 2 to the m times 2n plus 1, then minus 1. Okay, so let me explain the components. So the minus 1 is to get number 0, because unfortunately I count natural numbers from 0. Now this number is always non-zero. So to get 0, I have to shift everything by 1. Okay? Now, what's the meaning? Why do I have this? So remember so this is a number, right? This is number k. Remember a number k, for any number, we can factorize them into product of prime numbers, right? So the first prime number is 2. So you have a factor of 2 to the something. This m can be 0, right? And the rest is 3 to the power something, 5 to the power something. They are all odd. So the rest, no matter how many copies you have, the product is an odd number. So it is of the form 2n plus 1, right? So therefore, for each number, you can take out the most copy of 2's, the remaining one will be an odd number. So from the number, you can get m and n. Right? So this is the idea. Okay, so I define a function like this. I'm going to show you that this is injective and surjective. Okay, so since I skipped injective last time, let's do it together. Right? Okay, so suppose you know the injective, right? Injective means different points sent to different points. Or in other words, if you have 2 points with the same value, then the 2 points has to be the same, right? Otherwise, you have different points sent to the same point, right? Okay, so I take this form. Suppose the 2 pairs m1, n1 and m2, n2 send to the same place. I want to convince you m1 equal m2 and n1 equal n2, okay? Okay, so suppose we have this, the value are equal. By definition, okay, this guy take minus, okay, this guy with the subscript 1 is equal to the same thing with subscript 2. I cancel off the minus 1, right? Doesn't matter, but on both sides. So I get this equality. Okay, so now I first convince you m1 has to be m2. Why? Because let's say, suppose m1 is smaller, right? Let's say m1 is 2, m2 is 5. Now I can cancel off the smaller number of 2's, right? So here I can, suppose m1 is 1, I can divide 2 to the power of 2 on both sides, right? So this power is gone, but here I still have some copy of 2's, right? But that's a problem because after I cancel off all the copies on the left-hand side is an odd number. But the right-hand side, because of the extra copy of 2, it is an even number. So it's not possible. So therefore, if I want to cancel off, I must cancel both the copy of 2 to the... I must cancel the same number of 2's on both sides. So therefore, M1 has to be M2. Okay? Now, if you cancel the 2, the rest is easy, right? So if 2n1 plus 1 equal 2n2 plus 2, so you certainly get n1 equal n2. Okay, so it's fairly easy. Now, surjective, I want to say that every natural number will be the image of some pair. That's the meaning of surjective. Okay. If the number is 0, okay, f00 give me 0 because this is 0 time, this is 1, sorry. I claim f00 is 0. Why? Because if I plug in 00 here, the first part gives me 1. That's because of the minus 1, I get 0. So 0 is in the image. Now, if you are not 0, suppose a natural number is bigger than 1, is it an image of a pair? Well, I just explained. If the guy is bigger than 1, you can factorize the number in a unique way so that you can take out the number of 2's. The remaining one has to be an even number. So then you can get the mn so that it goes to the given number, right? I know here I'm a little bit rushed, but I'm sure you can do it if you go home. This is not hard. This is really okay. So now, actually, there's other interesting proof. I'll say the idea. You'll probably have seen people use this. I'll say the idea, and the proof is a little bit more complicated. So here, imagine we have, so these bullet points are the numbers in n cross n, right? Each bullet, so for example, this point is 1, 1, right? So this point is 2, 1, right? And so on and so forth. So each bullet point is a point on the n square. Now I want to show you the number of bullet points is the same as the integers, the natural numbers on the line. So I want to turn this two-dimensional picture into a very, very long line. Okay? So how do I do it? I start to build my line here from the corner. So this is my starting point. And then I move to this point, 1. Then follow the arrow, I move to this point. This point is 0, 1, right? 0, 1. And then I come down to here to get 2, 0. And then I follow the black arrow, I move to this point, 1, 1. And then I move to 0, 2. Right? Then I come down to this point. This is 3, 0. And then move this, follow the black arrow, go to there, and then come down and move and come down. So I have a zigzag. I have a zigzag line of follow the arrows. Is it okay? So now imagine someone pull this. Okay, so we have a thread, right, like this. So if I pull this thread from 0, this point, right, pull it to infinity, then everything on the plane will follow this line, right? So this is the way. Okay. Now to find the exact mathematical expression is interesting, but a bit long. So let me continue first. If I have time, and if you think I should give this, I will come back to this. Let's temporarily skip this to move on to the next part. Okay. Okay. So now, as you have seen, to find the exact match sometimes is quite difficult, quite clever, right? But we have other tools to help us. For example, this contour-Bernstein theorem is one of the tools. The theorem is a non-trivial theorem. You learn it in if you are math major students. Okay, but we just want to know what it says. Okay, so here, so it is often tedious or smart to define and verify it is a bijection. So can we show that two sets are of the same size without finding the bijections explicitly? Right? The answer is we can. We can use the theorem. Okay. So the theorem, before I show the theorem, I have to introduce a definition. So the size of A is less than or equal to the size of B. Right? The notation is the size of A is less than or equal to the size of B if there is an injection F from A to B. You see here, I do not need to match every element in B. As long as I can send elements in A into B in an injective way, I'm happy. So the intuition is the F will match A with a subset of B because it could miss some point in B. Right? So F will match elements in A into a subset of B. Okay. So this is the meaning of the size of A is less than or equal to the size of B, or the cardinality of A is less than or equal to the cardinality of B. Okay. Now the contour-Bernstein theorem says if I read it, it looks trivial, but it's non-trivial. Okay, so let me first read it. If you think it's trivial, fine. I mean, we are going to use the trivial side to prove things. Okay, it says if the cardinality of A is less than or equal to cardinality of B, and cardinality of B is less than or equal to cardinality of A, then they have equal size. Right? So you would think that, of course, this is obvious, but this is a non-trivial because here when we define the less than or equal to and equal to, we always talk about two sets at the same time. We never define what is the meaning of the modulus of A for infinite set. For finite set, we say we count. For infinite set, we haven't defined it. All we are able to do is we know which one is bigger than, we can only compare. We do not know the absolute size of a set. We can only say this guy is bigger than the other guy or they are the same, right? So if you read the definition, the contour-Bernstein theorem says, suppose you have an injection from A to B and injection from B to A, then suddenly you have a bijection between A and B. This is not trivial. I draw a picture to show you. Must be a way to. Okay, good. Okay, so just now I said this is A, this is B. Now suppose you have a map. Okay, A has 3 elements. B probably have more elements here. Suppose you have an injection from A to B, and then it means the size of A is less than or equal to the size of B, right? Because you only have an injection, you may miss because it's not surjection. So you may miss loss of point in B. So you only map A with a subset, right, with its range, f of A. So you match A with a subset of B. So the size of A is smaller or equal to B. Okay, so this is the intuition. Now, the contour Bernstein is something like this. So you have A, you have B. Now, you can map, you have an injection F from A to B, right? So you match A with a subset of B here. Now, for some reason, you also have another injection, let's say G, from B to A. Maybe you map B to somewhere here, right? So contour Bernstein will say, then there is a beautiful map which match A and B in a perfect way. From the picture, it doesn't look like that, right? So you only know there's a map from A goes into B, or no, there's a map from B goes into A. It doesn't mean you have a perfect match, right? To have a perfect match, you have to play around F and G a lot. So that's a non-trivial theorem. Okay. All right. We'll stop after I finish rational numbers, which is a couple of slides away. Okay, so this is a general education module, so we don't bother about exact definition of cardinality. Okay. So, but this is why I say this is useful, because, for example, if you want to show here the bracket means the interval. This is on real lines. If you look at real numbers between -1 and 1, and the closed interval, the real numbers between bigger than or equal to -1 and less than or equal to 1. Do you know intervals, right? You know the interval on the real line. Okay, so this round bracket means open interval. It doesn't include -1 and 1. This square bracket means the closed interval. It includes -1 and 1, right? Now, if I ask you to find a bijection between the two, it's a bit hard because you have the two extra points. Where do you map to? But if I use contour Bernstein, it's very easy because the identity map, this is a subset of, the open interval is a subset of closed interval. So the open interval is less than or equal to the size of the closed interval. Now, how about the closed interval is less than or equal to the size of closed interval is less than or equal to the size of open interval? You just divide everybody by 2. You shrink the closed interval to a closed interval minus half to positive half. And that closed interval was sitting inside here. So you match the closed interval with a subset of this, right? So immediately you get left-hand side is less than or equal to right-hand side, and right-hand side is less than or equal to left-hand side. So by contour Bernstein, you get they are equal. So you can see this is much easier. Can I draw it out? Okay. Yes, we can. Okay, so come on. Okay, so here I have a real line, and I have -1 and 1. Here's 0, right? Now I have another interval. Right, so I have a black object, I have a red object. Red is between the bracket, exclude the 2 points. Okay, the closed interval includes the 2 points. Okay, Now, let's call this set A, this set B. Okay. So I define f of x equal x. So this is, f is from A to B. You just, because the closed interval has 2 extra points, so obviously the open interval is, the size is smaller, less or equal to, right? Are you with me up to here? Okay. Now the other part is slightly more interesting. So I'm going to shrink this to minus half and half. So I define G from B to A by G of x equal half of x. Right? Everybody here just divide by 2. Okay? So then the divide by 2 is like scaling down. Right? So you shrink the interval into a smaller interval. And then the smaller interval will sit inside here. So you match B with a subset of A. Right? So you don't care what happened here. So this G will demonstrate B is less or equal to A because you have this injection. Now Counter-Bernstein will tell us then these two guys have the same number. So it's much easier, right? So Counter-Bernstein will say because of 1 and 2, and then suddenly A is the same as B. Okay? So hopefully I answered the question. Okay. So now this is my target. I want to convince you the rational numbers have the same size as natural numbers. Okay? So the rational numbers are the quotient, are the ratio of 2 integers. Now, ignore the slash. Just think of them as coordinates. So it's like the integral point on the plane with lots of repetitions. For example, 1 divided by 1 is 2 divided by 2. But never mind. So the rational numbers, the positive rational numbers, is less or equal to the points on the plane. So therefore, we have shown these are equal. So the positive rational numbers is less or equal to this. Now, obviously, the size of natural numbers is less or equal to the positive rational numbers, right? Because there are so much more. I mean, there are lots of ratios, right? So by Counter-Bernstein, you'll know that the size of natural numbers is equal to the positive rationals. Now, there's a small step. Convince yourself if you add in the negative rational numbers, it's the same size as the positive rational numbers. So for those who are good at math, right, try this. But this is general education mode. You don't need to show this, right? Just convince yourself is the case. Okay, so before the break, I want to introduce this so that you can think of something in the break. So let's define the size of A is strictly less than the size of B. If it is smaller but not equal, right? This is reasonable. If it's strictly smaller, then it means it's less or equal to and not equal. Okay? Now the question is, do we have two sets of different size? Two infinite sets have different size, right? Maybe all infinite sets have the same size. One size fits all, right? We have squeezed in integers into natural numbers. We squeeze in rational numbers into natural numbers. Maybe we can squeeze everything in, right? So here's a challenge for you. Are there any infinite set having size larger than natural numbers? In other words, can Hilbert Hotel be full? I mean, suppose you have a bunch of guests, then Hilbert Hotel cannot settle these guests. Does this ever happen? Okay, so let's take a 5 minutes break, and then we'll see the answer. Okay, so there are questions about how I line up the points on the plane to natural numbers. It takes a while to digest. So if you have questions about that, ask me after I finish. So I'll continue. So these things, if you see it, you see it. If you don't see it, it takes a while. It's quite difficult because it talk about infinity. So it's but anyway. So let's try. Let's continue and see what how far we can go. Okay. So the question for you is there only one size of infinity? No, okay, but it takes an even harder argument, a clever argument to show this, right? So the answer is the size of real numbers will be larger than the size of natural numbers, okay? So let's consider this interval 0, 1, which is a subset of real number. So if I convince you that there are more real numbers inside this interval than natural numbers, then real number itself will be more than natural numbers, right? Okay. So now why do I shrink it to 0, 1? Because element in 0, 1 has this nice property. It can be written as a decimal, infinite sequence of decimal. It has an infinite decimal expansion, right? So I can write the points between 0, 1 as 0 dot A1, A2, A3. For example, A1 could be 1, A2 could be 2, right? Something like this. A3 could be 0, and so on and so forth, right? Okay, so, well, this part I don't care. It is Cantor, the guy event set theory. He showed that the number of elements, number of points in 0, 1, interval 0, 1, is strictly bigger than the size of natural numbers. Okay? Let's see how he does it. So this is one of the most beautiful theorems in the elementary mathematics. Okay, so we show the real numbers in the interval 0, 1 cannot be listed like R1, R2, dot, dot, dot. Right? You cannot label them by natural numbers. No matter how hard you try, you always miss somebody. So there's no bijection. Okay? So any list like this is not exhaustive. I'm going to show this. I'm going to convince you this is the case. No matter how smart, no matter how you thread the points, you cannot exhaust the interval 0, 1. Okay? So you give me your way to match. I will show you you are going to miss something. I will return you an exception point. Okay, so show me your plan. I will show your plan doesn't work because here you get a point. You didn't match, right? So this is the argument. So the method is called diagonal method. It's extremely useful and in mathematics. Okay, people use it over and over again. Okay, so here is a detail. How do I convince you? No matter how hard you try, you just cannot exhaust the interval 0, 1 using natural number many points. Okay? So how do I do this? So let's assume you have your wonderful candidates like R1, R2, dot, 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 right? This is your list of the numbers in the interval. Okay? So I want to show you that you miss some point. So this argument is called diagonal argument because I can draw a picture like this. The real proof will continue to the next slide. Okay, so now I want to present your R1, R2, dot, dot, dot in this way, right? Because R1 is a point between 0, 1. So R1 will have his decimal expansion like this, okay? Now, the next number is R2. R2 will also have its decimal expansion. So the digit I indicate, for example, A21 means the first 2 is the expansion of R2. The second one is his first decimal place, right? So we'll see an example in two slides down, okay? Okay, so you list out R1. Let's assume R1 is this. Say R1 is 1415 or something. R2 is 3219 and so on. Okay, so then in general Rn you have this. Right? Now I want you to pay attention to the diagonal position. So I want to show what you miss by do some operation on this diagonal position. Okay? You are with me for the setting, right? So this is a candidate of exhausting all the real numbers between 0 and 1. Okay, so these are the candidate. I'm going to refer to this picture, produce a new number, which is also between 0 and 1, and I claim my number is not on this list. Okay? So here's my number. So I define my number B in this way. It's 0 dot, again by some decimal things. So I'll do things against you do. So the nth position, my nth position, will be 1 if your position is 0. And if your digit is not 0, I will be 0. I just do things against you at the diagonal position. Okay. I want to convince you this B is not in your list. Now, maybe this is too hard to digest. Let's see the example. So suppose your R1 is, let's look at concrete decimal. So maybe it's 0 all the way. Maybe your R2 is 01 all the way. The example may not be too accurate. Maybe you can change somewhere here. So this is not strictly between 0 and 1, but just change some digit. It will be inside. So this is just an example. Okay. So suppose your R1 is this, R2 is that, R3, okay, something like this. R4 is like this. Okay, R5. So I also use binary for simplicity. So you have your possible list of all real numbers inside the interval 0, 1. Okay? Now, how do I construct my B? So my B will have 0 dot something. Now, my first digit, I go against R1. So I look at the R1's first digit. Which digit are you? You are 0. Oh, I take 1. Okay? Now, for R2, okay, I already fixed my first digit. I cannot use my first digit to do anything against R2. Well, I have second digit, right? So look at R2's second digit. Oh, it is 1. Okay, I define my B. The second digit is 0. You understand, right? Now look at 2 more, maybe R3, right? R3 looks like this. What is your third digit? Okay, third digit is 0. Well, I'll define my third digit to be 1, so that I will be different from R3, right? One more, right? R4, okay. So what is your fourth digit? Okay, so 0. Okay, it's 0. Now my first digit is not 0, it's 1, right? And so on and so forth. So look at diagonal position and define your number at the diagonal position just against the nth element. Use your nth digit to diagonalize against the nth element. I hope the example will help you to see what's going on, right? So come back here, what I did is this. So I choose my Bn so that my Bn is different from Ann, right? If Ann is 0, I'm not 0. If An is not 0, then I'm 0. So my nth digit is always different from the nth digit of the nth element. Okay? So the claim is if I define my B this way, my B is not equal to, it does not appear in the list. Well, obviously, I just create a difference, right? For example, here, this B is not any one of these, right? To see B is not R5, just look at the fifth digit. The fifth digit, R5 is 0, my B will be 1, right? For each number in this table, I have one digit which is different. So this B does not appear at all in this picture. So that shows no matter what you put in this big table, you always miss something, which is something like this B. Right? This is smart, right? So, okay. Okay. So that shows at least there's one, infinity at least have two sides. One is the size of natural number, the other one is the size of real number, right? So at least two sides. Now Cantor showed much more. Cantor showed that you always have some larger size. So this is a short but beautiful proof. It's like the Russell paradox. Let me go through it. So if you have problem, I'll be very happy to talk to you after class. But let's see what he says. So he says this: for any set X, there's always some set which has larger size. So the set have larger size is just its power set. You collect all its subsets, that set will be larger than the original set. Let me read it. For any set X, let Y be the power set of X. In other words, Y collect all the subset of X. We have seen the example of this, right? So then the size of Y will be strictly bigger than the size of X. So in other words, you can always get larger and larger size. So the size, so the infinity have lots different size. It's just we live in a small world. We didn't see them. No, we don't encounter them every day. Okay. So the proof. Let me go through the proof. It's a bit interesting. Okay. So the proof goes like this. It's the same idea. So I want to show Y has bigger size than X. I'm going to claim that you cannot match their elements. No matter how hard you try, you'll miss somebody. Okay, so let's see the proof. First, it's very easy to see that the power set has more elements, right? Because for each X, you just send it to the set of X. Then this set of X belongs to the power set. So at least you have an injection from X to power set of X. So I think you believe me that power set has lots more elements, right? So this is first the size of X is less or equal to its power set. Now how do I show? This is difficult. This is the smart part. How do I show that the size of X is not the same as size of power set? So I'm going to use the same idea to say that any function try to match X and Y will not be surjective. Onto is another way of saying surjective. This is the same as what we did for the diagonal, right? We say that any attempt to match natural number with the real number between 0 and 1 will not be exhaustive. Here, we do the same thing, the same logic. Any attempt to match X with its power set will miss some set. No matter how hard you try, you are going to miss some set. So therefore, you cannot have a bijection. You cannot have a surjection. Okay? Okay, so the proof is even shorter. So consider the set S. So you give me your candidate, right? Your candidate F is trying to match X with its power set. I'm going to show you miss somebody. So this is the somebody you miss. Okay, the somebody I define to be S. He collects all the small x in big X such that X, small x, is not a member of the image. This is a little bit like Russell's paradox, right? So okay, so let's figure out what it is. So f of x, f is from x to power set. So f of x is a subset of x, right? So it makes sense to talk about small x. Are you in the set or are you not in the set? Okay? So I will collect x if you are not in the set. If you are in the set, I do not take. So it's like a diagonal argument, right? I'm going to against you. If you take in this way, if somehow you satisfy this, then I don't take you. If you belong to that set, I don't take you. If it doesn't belong to that set, I'll take you, right? So I'm trying to do this diagonal things again, right? Okay, so this is a bit abstract, I know, but it's so short, you can do it. Okay, so this is the example I'm going to show you. We claim that this S you are going to miss is not in the range of F. Why? Suppose it's in the range of F. So suppose this S is F of Z, of Z, for some Z. Okay? So suppose this S is in the range. It is F of Z for some Z, right? This is the meaning of in the range. Okay? Now, if you have this Z, I'm going to ask this Z, are you in S? Okay, so then we have a funny equivalence. So the answer will be Z is in S if and only if Z is not in S. That's ridiculous, right? You are in if you are out. You are out if you are in. Then this is certainly ridiculous. So let's see how we get this. So suppose Z is in S, right? Now, what is S? S is Fz, right? Because you choose your Z to be Fz equal S, right? So you just replace this S by Fz. So these two definitely equivalent, right? Okay, one more time. I claim Z is in S is the same as Z is in Fz. Why? Because I assume S is Fz, so I replace S by his equivalent version, Fz, right? So we go from here to there. Okay, so, right? Now, I want to go from here to there. Why? Because if Z in Fz, so Z is in Fz, right? Z is in Fz, then I will not take it. I is S, right? S will not take it. Okay, you see, by the choice of S, S will only take those which are not in F of something. So if Z is not in Fz, then S will take it. If Z is in Fz, then S will not take it. Right? Are you? So this is by my design by the choice of S. So from Z in S, I get Z not in S. Now this is if and only if, right? So now from Z is not in S, I get Z in S. So this is, no matter how hard you try, is wrong, right? So this shows you cannot, this shows that S is not in the image. Okay, so this is well, not everybody is Cantor, so this is a bit strange but interesting. So the conclusion is there's no set with largest size because its power set will always be larger. Okay? So now, okay, we don't have time, we skip this. Now I want to finish by use 5 minutes to finish this funny topic. So there's something called continuum hypothesis. So we have seen the size of natural number. We have seen the size of real number. Okay? Now the question is, are there any size in between? Yes. Okay. So this is called a continuum hypothesis. So if you say yes, if you say yes, then that means continuum hypothesis is not true. Okay. So continuum hypothesis says there's no size in between. So the continuum hypothesis, abbreviated as CH, stands for there's no size between natural numbers and the size of real numbers. So in other words, if you are strictly less than real number, the size of real numbers, and then you are at most as large as the natural numbers, because there is nothing in between. If you fall off real numbers, you have to be less or equal to the size of natural numbers, right? So this is one way of saying continuum hypothesis. Okay? So this is an important problem. Hilbert, in 1900, he gave a lecture in the International Congress of Mathematicians. He lists 23 problems. So this is his number one problem. And in the past 100 years, it gets solved. Right? So I'll show you the history. So this is a mathematical problem, and it's very important. Right? Now, before I move on to the next slide, do you think this one has an answer? Do you think this is either yes or no? Right? You all believe it definitely has an answer, right? What do you think? Right? Yes, yes. So you are all so-called Platonists. So in philosophy, you belong to one school called Platonist. I'll say that in a moment. So let me continue to finish. Right? So you understand the problem. It's very easy to see. Right? Whether there's a size between real numbers and natural numbers. The size means the bijection and all these things. Okay? So now, this question turns out to be, okay, so I'll skip these. So I'll skip these. I'll skip this. So it turns out to be the continuum hypothesis is independent of ZF. Okay, so the axiom of set theory, we mentioned it, right? It's called Zermelo-Franco with choice, maybe. So Gödel showed that from set theory, you cannot refute is a way to prove it's false. So from set theory, you cannot demonstrate the continuum hypothesis is false. And then Paul Cohen showed this is Gödel's result is in 1938, and Cohen's result is in 1963. Okay, so Cohen showed from set theory you cannot prove CH. So CH, if it has an answer, it's beyond set theory, and set theory, as we believe, is foundational mathematics. It includes almost all branches of mathematics. So in other words, to settle this CH, such an innocent problem, you need something more difficult, beyond set theory, beyond everything you'll learn in NUS in 4 years or 8 years. Okay, so here's Paul Cohen. He's the only logician who gets Fields medal. And so he got Fields medal because of the work. Okay, so now is this the end? So we know that continuum hypothesis is independent. Now, for those who think you have an answer, right? It must have an answer. So how do we get the answer, right? Okay, so after this, there are two schools. So one school think this question actually is meaningless. It has no truth value. So why it is so? So this is again related to philosophy of mathematics. So some people believe mathematics, especially about infinity, they are not real. They do not exist in the physical world. So it's our fantasy. So for something like a fantasy, there's no truth, right? You can imagine something. So you can imagine it this way, you can imagine that way. So some people think CH shows that higher infinity is fantasy. If you get to the world of infinity, you can do it this way, you can do it that way, no truth, right? But people like you, right, for those who just say yes, 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 or like Gödel, so they believe that no, CH must have an answer. So I don't know what you think, but Gödel think mathematical objects are real. It's just like table, like this bottle. Mathematical world is just like physical world. So there is a reality inside mathematical world. So against this reality, CH, right, is either true or false. It's like this bottle is either on the table or not on the table, right? So you must have an answer. So we don't have an answer only because the set theory axioms are not adequate, right? So there's a reality. Set theory is trying to describe the reality. Now, set theory is unable to decide CH only because set theory at this moment is not adequate, is not sophisticated enough, okay? So Gödel believed the role of CH is to lead people to discover new axioms, right? So the current axiom of set theory is unable to determine CH, but let's continue to work, try to find some new axioms so that when we add a new axiom to set theory, we'll solve the problem CH, right? So then currently there are still, this is still active branch in set theory. Okay, so I'll finish by making this remark about the Platonist. So if you think set theory describes something real, and then you are Platonist. So this comes from the Greek philosopher Plato. He believed all the abstract concepts are somewhere there. Okay, so if you think questions like CH definitely have an answer, you are probably belong to that camp of philosopher. So there are other camps, but anyway, so I skip lots of slides. So if you tolerate me, I want to tell you just one more slide, not to prove, not everything. So is this slide about Cantor's notation. So Cantor actually developed lots of things. So Cantor used this word aleph to denote the size of infinity. So aleph is the first Hebrew letter. So he used this aleph for the cardinals, right, for the size. So the first infinite size, which we know is the size of natural numbers, he denoted by aleph naught. So this is aleph 0, which is the smallest size of infinity. Okay, and then so for some of you know this is also called countable. If a set has this size, it is called countable. Okay. Now the first uncountable size is denoted by aleph 1. So after aleph 0, you have the next size called aleph 1. And then you have aleph 2, aleph 3, and so on, right? So Cantor is a very strange person. He believed that his alephs are stairs to God. So the God is the complete and absolute infinity. It's because he has this theory of infinity, right? So these alephs are getting larger and larger, so when you goes up, according to this stair, you get closer and closer to the absolute infinity, right? So this is interesting. I guess people are going off. So if you have questions, I'm happy to talk to you. And otherwise, happy Chinese New Year. See you after New Year.